Hello, I am Serdar Erişen. I'll present SERNet-Former Semantic Segmentation by Efficient Residual Network with Attention Boosting Gates and Attention Fusion Networks. In this research, it is aimed to develop an encoder-decoder architecture with additional methods to improve the performance of the network by regarding the multiscale problem and fusing semantic information from different contexts. Fusing the multiscale semantic information is one of the compelling issues in segmentation tasks, besides the concerns of computational cost and efficiency of the developed networks and methods. Recently, generative AI ranging from large language models to vision transformers, swim transformers continued to set state-of-the-art performances in computer vision tasks. On the other hand, computational cost has become another challenge to deal with and develop real-world applications. So this work re-evaluates the efficiency of the CNN-based encoder-decoder architectures with additional methods, and the spatial information and feature maps in CNNs are aimed to be discovered deeply for efficient and precise semantic segmentation in this work. So regarding the problem of rising computational cost, the research dives into the deep potential of the improved performance of CNNs with attention-based fusion networks and modules, as they can also be improved and scaled into huge baselines. So it is first explored to find the most efficient baseline architecture that can be trained fast and should be lightweight. It is found that residual networks pre-trained on ImageNet dataset can be the most efficient and fastest baselines to be improved in learning most of the classes in FEV pools, even if they can have capacity problems for new features. So it is started to explore and develop residual networks as the baselines for further improvement on the encoder network. And the exploration of efficient encoder for fast and accurate training without losing the existing progress of baselines, attention boosting gates and attention boosting modules are designed to excite and fuse the feature-rich spatial information into the existing networks. Respectively, our encoder is advanced by introducing attention boosting gates to the residual networks. In the usual deployment of attention layers, it is normally compressed into the feature-rich and lower-dimensional representation maps, and the information is reshaped back into the input with the same sizes of the width and the height. On the contrary, attention boosting gates increase the probability of exciting the equivariant feature-rich semantic information from the selected baselines with the equivalent sizes of the input and output in our work. So the sigmoid function, which is widely applied in attention networks, increases the possibility of acquiring and processing equivariant channel-wise and feature-based rich semantic information that could not be activated in the commonly used residual network architectures. So the attention boosting gate works as a mathematical operator for exciting and fusing the feature-rich semantic information without rescaling the semantic information, and we get the feature-rich scalar values like super thin squeezed attention maps and like eigenvalues from the input. So based on operations of sigmoid function, it is also possible to increase the attention-based capacity of the network further, as the model can also be scaled to several billions of parameters, which are not preferred in the study due to computational cost. Attention boosting module fuses the acquired and processed feature-based semantic information with the spatial context of the residual networks by element-wise addition. The feature-rich semantic information is fused with the spatial context of the encoder by attention boosting models, which result in a novel efficient residual network, Efficient-ResNet. To provide an efficient transition between encoder and decoder networks of the developed architecture, dilation-based convolution layers are used. They are applied to increase the probability of searching, recognizing, and comparing the local, channel-based, and rich semantic information between the encoder and decoder parts by decomposing the output into smaller feature maps. The output of the encoder architecture is moved into the convolution layers with 12, 16, and 18 dilation factors, together with the following batch normalization and ReLU layers. Attention fusion networks are introduced into the decoder for processing the semantic information with the global and local contexts from the encoded part. It is also aimed to increase the capacity of storing semantic information in the decoder regarding the limitations of smaller and simpler residual networks. Inspired by the methods used for the boosting gates, the efficiency of diffusing global and local context into the decoder part is improved by attention fusion networks. Even though the initial layers of CNNs are rich in the global context of semantic information with sharp edges and apparent shapes, it is significant to transfer and reconstruct the feature-rich spatial information from the encoder during the upsampling tasks in the decoder for efficient and one-to-one image processing. So attention fusion networks are designed with the convolution layers and the spatial and channel-based contextual semantic information from the convolution layers with different strides are gathered by the concatenation of the products of fusion networks via the depth concatenation layer. In that regard, skip connections are used to increase the efficiency of the network in acquiring the spatial information from the encoder concatenated with the channel-based features during the upsampling operations. In brief, our network is developed from the residual CNNs by adding attention boosting gates and attention fusion networks. Our additional methods are connected to the encoder and decoder parts via skip connections to fuse the rich information from different contexts concatenated by superposing the useful semantic information for the highest efficiency. To the best of our knowledge, an efficient residual network is developed that is unique in the literature, and the network is improved by attention boosting gates and attention fusion networks with increasing efficiency and precision in predicting and recognizing smaller objects and their features. Our methods show significant improvements in the trained baseline architectures in the initial epochs on CamVid dataset. During the experiments, different baselines of DeepLab v3+, such as ResNet 18, 50, 101, Exception and Inception ResNet v2, are also trained in MATLAB and compared to the results of our network. So figures illustrate the comparison of the initial training performance of some networks using CNNs as the baseline architectures. Respectively, SERNet-Former learns much faster than the quickest baseline that is applied in the DeepLab v3+ architecture during the training sessions on CamVid dataset. So CamVid and Cityscapes datasets are explored to test the performance of our network, and here are the results for CamVid dataset, and the details about the inference of the model are explored in the paper of this work. The performance results on Cityscapes dataset with the breakdown of class accuracies and comparison with the earlier state-of-the-art methods are as follows. Finally, ablation studies are conducted to analyze the contribution of each method, which are performed on CamVid dataset during the development progress of the network, saved as checkpoint. And here we see the impact of attention boosting module added to the last convolution block of the encoder, which augments the feature-based and channel-wise contextual semantic information of the network and increases its efficiency by 1.66%. Accordingly, the dilation-based network increased the performance of SERNet-Former by 2.3%. An attention fusion network is introduced into the following the convolution layer with the stride 1, and it adds up to 3.89% to the overall test performance of this checkpoint. When the fusion network is implemented into the decoder, or in other words, removed from the network, with the following the convolution layer with the stride 4, it improves the network's performance by more than 7.5%. Based on the earlier test results, Fusion Network contributes to the improvement of SERNet-Former by 9% as it also processes the spatial information with different sizes and contexts. In brief, attention boosting gates and attention fusion networks, in which the sigmoid function is used to increase the possibility of activating the channel-based feature maps, improve the efficiency of the network with the rising performance by fusing semantic information from the local and global contexts. So, Efficient-ResNet is still open to be improved and tested on the challenging datasets for classification tasks as the encoder of SERNet-Former. The decoder part of our network can also still be modified with attention fusion networks. Additional methods that are not applied during the experiments, such as multi-scale crop size of images and transformers with larger attention heads, will also improve the results of our network. So we hope that our methods applied in Efficient-ResNet and SERNet-Former inspire many researchers to develop novel and efficient state-of-the-art deep learning architectures. Thank you.